Welcome in Mechanical System Design. I am Professor A.P. Godke, Assistant Professor in SND College of Engineering and Research Center at Department of Mechanical Engineering. Today we will discuss about the unit number 6 of our subject Mechanical System Design, that is the optimum design. So in previous session we already know what is the optimum design, what are the parameters that are considered under the optimum design, then what is the adequate design. Now we will see the methods of optimum design. So first we will see the Johnson's method of optimum design. So it is one of the oldest method of optimum design. In any design procedure, a number of design equations are used. In this method, design equations are categorized in 3 categories. So this is the method of optimum design. So it is the oldest method. And then if we consider any design procedure, number of design equations are used. And in Johnson's method, design equations are categorized in 3 types. So first type is a primary design equation. It is also called as a PDE, primary design equation. So the most important, it is the most important design equation. It is nothing but a target equation. It is also called as a target equation, primary design equation. It is designated by PDE. So primary design equation is designated by PDE. Then it expresses the most significant functional requirement to be maximized or the most significant undesirable effect to be minimized. Means in primary design equation, so the which one is the most significant functional requirement that to be maximized is expressed in primary design equation, and the most significant undesirable effect to be minimized in primary design equation. So it expresses the quantity upon which the particular optimum design is based. So for example, primary design equation for airplane shaft requires to minimize the weight, which is the most significant undesirable effect to be minimized. Therefore, the equation which expresses the shaft weight is Wt is equal to mass into density is equal to area into volume into density. So this equation is called as a primary design equation. The weight of the shaft is can be represented in the form of mass and density. That is nothing but mass can be represented in area into volume and density of the material into acceleration due to gravity, that is 9.81 meter per second. So then design of gearbox for minimizing size, the equation which expresses the size which is most significant undesirable effect to be minimized, size of the gearbox is limited by center distance. So here center distance equation is represented by Rg plus Rp. That will be equal to dg plus dp by 2. That will be equal to m zg plus m zp by 2. That will be equal to m zp by 2 into 1 plus g. So the primary design equation is expressed as PDE, most significant functional requirement or most significant undesirable effect, is equal to function of functional requirement including undesirable effect, comma material parameter and geometrical parameter. So this is the representation of primary design equation in Johnson's method of optimum design. Second is second category is the subsidiary design equation, that is designated by SDE. It is the design equation other than primary design equation. So it is either express functional requirement or undesirable effect. Therefore, for example, stress equation, the equation of the stress is called as a subsidiary design equation. That is nothing but sigma T is equal to force upon area. Is we consider it as a stress equation, which is called as a subsidiary design equation. Though, so the subsidiary design equation is expressed as SDE is equal to a function of functional requirement parameter including undesirable effect, comma material parameter and geometrical parameters. Then third category of the Optimum design equation in the Johnson's method of optimum design is the limit equation. It is designated by LE, that is the limit equation. These equations give the satisfactory range for the value of certain parameter. So this will give the maximum and minimum or some limitation or limit for the value of certain parameters. For example, here circumferential stress or tangential stress is equal to SUT upon NF. That is nothing but sigma T is allowable or circumferential stress. SUT is the ultimate tensile stress, and NS is or FS is the factor of safety. So this equation is called as a limit equation in the optimum design. Next, categories of optimum design problem. So according to the Johnson's method, any optimum design problem comes under one of the following category. First one is a normal specification, second one is a redundant specification, and third one is a incompatible specifications. So we will see one by one. So optimum design for normal specification is, in this type of problem, it is always possible to combine all the subsidiary design equation with primary design equation without eliminating or ignoring the limited or specified parameter. So this is the simplest case of the optimum design. So in this, a number of free variables are greater than or equal to number of subsidiary design equations. So the total variables is equal to number of free variables plus number of constraint variables. So free variable is nothing but what? It is one with the no constraints imposed by the limit equation. That is, unlimited or unspecified parameters are also called as a free variables. Next, optimum design procedure for normal specification. In normal specification, first step is to identify given parameters, write down all parameters, then write a primary design equation, subsidiary design equation, and limit equation. Then combine subsidiary design equation with the primary design equation and eliminate specified unlimited parameters and write develop PDE, that is a primary design equation. Then combine a limit equation with the developed new primary design equation. Then determine optimum quantity from final primary design equation. So in this way we can do the optimum design using the Johnson's method of optimization. Now we will see one example here. So a simple tension bar having circular cross section is subjected to a tensile force P. Design the bar with the objective of minimizing the material cost using factor of safety N. The following limitations are specified in the optimum design. Assume suitable notation, that is L minimum is less than or equal to L is less than or equal to L maximum. So in diagram you can observe one bar is there, which is subjected to a tensile force P. Then L is the length of the bar and A is the cross sectional area of the bar. So here P is the tensile force, capital N is the factor of safety. Then our objective is to minimize the material cost is our objective. Therefore, the design parameters, so here CM is the material cost for the tensile bar in RS. Then C is the cost per unit mass for the bar material, RS per kg. Rho is the mass density of the bar of the material, kg per meter cube. A is the cross sectional area of the bar in meter square. Then L is the length of the bar in meter. Then P is the tensile force acting on the bar in Newton. Then N is the factor of safety. Sigma T is the tensile stress induced in the bar, Newton per meter square. SYT is the yield strength of the bar material in Newton per meter square. So in first step, what we perform basic configuration of the sketch and given parameter, and in second design parameters are noted down. In next step, in third step, we have to develop the primary design equation. So the most significant undesirable effect to be minimized is the material cost of the bar. Therefore, Cm is equal to cost per unit mass of the bar into mass of the bar. Therefore, C is the cost of the bar and density mass of the bar is rho A and L is the length of the bar. Therefore, Cm is equal to rho C rho AL in RS. So this will be called as a primary design equation. Next step is the subsidiary design equation. That is the design equation other than primary design equation is the tensile stress induced in the bar. So that will be denoted by sigma T is equal to P upon A. So this equation is called as a subsidiary design equation. Next is the limit equation that it is the satisfactory range for the values. So that will be the tensile stress is less than or equal to SYT upon N, and limit equation is a L minimum is less than or equal to L is less than or equal to L max. So these two equations are called as the limit equations for the range of the values. Then the classification of parameters, so functional parameter, specified parameter, limited parameter, unspecified and unlimited parameters. So we make the table. So in functional requirement parameters, specified parameters are force and factor of safety. Undesirable effect parameters are limited parameter sigma T and unspecified parameter Cm. The geometrical parameters comes under the limited parameter L and unspecified is area. And material parameters are cost, then density and SYT, that is ultimate tensile strength. Then combining SD and PDE. So here SD is subsidiary design equation and a primary design equation by eliminating the unspecified and unlimited parameters. So here Cm is equal to C rho AL and sigma T is equal to P upon A. Just combining it, you will area will be get cancelled. Therefore, C rho PL upon sigma T. So this is new developed the primary design equation by combining the original primary design equation and subsidiary design equation. So equation E shows that there is the effect of limit equation C and D developed by primary equation. This is the case of normal specification. Next, combining a LDA with the new primary design equation. So from developed primary design equation, Cm is directly, not directly, Cm is the inversely proportional to 1 upon inversely proportional to sigma T. Hence, for the minimizing Cm, the parameter sigma T should be placed at the upper limit, that is SYT upon L. Therefore, Cm is directly proportional to L. Therefore, Cm is equal to 0 P L minimum upon SYT upon N. So after solving this will be Cm is equal to P into N into L minimum into C into rho by SYT. So this is called as a final primary design equation. To minimize the Cm, the material selection factor C rho upon SYT should be minimum. Then selection of the material selection factor C rho upon SYT is calculated for all the available materials and the material with lowest value of C rho and SYT is selected. Then finally determination of the elimination parameters. The eliminated parameters A can be determined by using the SDE equation B, substituting by the limit value of sigma T in equation B. Therefore, yes, sigma T is equal to P upon A. So SYT upon N is equal to P upon A. So we will get the area Pn by SYT. Then finally determination of optimum quantity. The most significant undesirable effect to minimize the cost Cm is determined by using the final primary design equation. So from equation A and B, that is a primary design equation and subsidiary design equation, number of free variables are equal to 1. NF, that is factor of safety. Then subsidiary design equation NS is equal to 1. Therefore, NF is equal to NS. This is the case of normal specification. So in this way, we can solve the problem on the normal specification by minimizing the cost of the material with the following limitations are specified in the optimum design.